Okay. Good morning. We're in this class, we're going to talk about a multi-view structure for motion. The problem is formalized as follows. Given M images, we want to find all the cameras, M cameras, and as many as possible three-dimensional points. That's the setup. The core of the problem is the following: given point tracks. So given the images, we want to somehow extract features and correspondences so that we get point tracks, sequences of points that appear in different images. All of them are projections of the same three-dimensional point. So given point tracks, we want to compute the cameras, which may be projective or calibrated or uncalibrated, and three-dimensional points. Usually, we want to, in most methods, we want to optimize a bundle adjustment cost of the type that is seen here. So given the projections of the three-dimensional point, hold on a second. Oh, I'm not in display mode. Okay. Sorry about that. Okay. Okay. So the projection of the three-dimensional point, we want to fit as much as possible to the point tracks that we see in the images. And typically, we minimize a square norm. And so that's what we want to do. The problem is that bundle adjustment has many local minima. Many of them are bad minima. And so we need some way to initialize a bundle adjustment. And that's really the main part of the algorithms, of all the algorithms that are suggested for this problem. And secondly, we want to be robust to outlier matches. Usually, we match points based on local properties, and those lead to many erroneous matches, and we want to discard these wrong matches. And we will be speaking about three main methods. The first one is called sequential or incremental method. Secondly, we will speak about projective factorization. And lastly, we will talk about global averaging methods. So let's start. Okay, so incremental SFM is basically built around the following pipeline. Given M images, the first thing we do is feature extraction. We learned about that using Harris features or SIFT features, and many other similar approaches. The next step is to match pairs of features. Now, matching all pairs is expensive.
Monan, we still see the same slide. Is it okay?
Really?
Yeah.
You see the slide with the bundle adjustment, I suppose.
Yeah.
Okay, now do you see a different slide?
No.
No. So that got stuck. Let me try again. Do you see the pipeline?
Now it's okay. Now it's okay.
Okay, let's see if tell me if it doesn't work. Okay. So again, incremental SFM, we're speaking about the pipeline. First, we do feature extraction with Harris or SIFT. Then we want to match pairs of features. We saw how to do that with SIFT. One of the problems is that matching all pairs can be expensive. We usually think of dealing with many images, hundreds, maybe thousands of images. And so we can easily have tens of thousands or hundreds of thousands of features. So matching all pairs will be expensive. And so we might want to use some hashing technique to make this more efficient. Okay. Next, we have a step of geometric verification. So the idea is simple. We use ransack to compute essential matrices. Okay. And while we do so, we can eliminate outlier matches. Okay. And also we remove images if they have very few inliers. Okay. And the main step is the step of incremental reconstruction, okay, which proceeds as follows. First, in the initialization, we choose two of the images. We choose them such that they have many common inliers, okay, and then use them to recover camera parameters and 3D points for the two images. All right? This is the initialization. And next, we repeatedly do the following thing. At each step, we choose one image, again, based on how many inliers it has in common with the views that we already used. Okay. Then we use PNP to solve for camera pose. PNP is a name for matching three-dimensional points to two-dimensional projections, okay, using endpoints. Okay, so so far we build some structure with points. We hope that we have enough many inliers that are common with the reconstructed points and with the new image. Okay. In fact, we need at least 3 inliers here. And with 3 inliers, we can solve for the new camera pose. Okay. And typically, what people do is apply P3P, which you studied, with ransack, and therefore remove outliers. Okay, so we don't just count on the outliers we removed in the first step when we computed essential matrices. We again try to remove more outliers. Okay, so so in this step we sorry, again I want a pointer. Okay, we compare the existing reconstruction with the new image and determine the new camera pose using P3P and ransack. Okay. Next, we do a step of triangulation. Somewhere. Okay. A step of triangulation. The idea is that we want to expand our reconstruction. Okay, so so now we take more correspondences between the new image and the images that we already handled, and triangulate new 3-dimensional points. Okay, do you understand the difference between these two steps? So.
No.
Which points are used in the first step and which ones in the second step? Anybody understood that?
No.
So I thought so, and I want to repeat this. Okay, so in the first step, we need to take points that we have the 3D location of them, okay? And match them to the 2D projection in the new image.
How do you know that they are relative? The 2D and the 3D are matching.
Can you repeat?
You are saying that I have a new image,
Yes.
okay, and I have 2D points with shift, okay.
Yes.
How do I know that the 3D points that I found using 2 images are the same as the the shift point in
Yes.
2D?
Okay. Yes. So what's not written in the pipeline is that we try to extend the pairwise features into tracks, into point tracks. Should have written that. And the idea is very simple. So if a point A in one image matches point B in the second image, and point B in the second image matches point C in the third image, I make it a track. So basically, I'm looking at the pairs, and if the pairs share a point or the points are very close, let's say within a pixel or something like this of one another, I will make them a set of or a track of points. Okay.
But what if like point in the image C is match other point in image A, not like
right.
the
So
first
that
one?
would be used in the triangulation. Okay, so in order to actually get a three-dimensional point, I need to have matches between two points in two images. If I want to then extend it to more images, I will essentially, in this method, need 3 points at least. In the averaging techniques, we will see that you don't have to do that in order to do all the reconstruction. You can use only pairwise correspondences. However, pairwise correspondences will not work if the scene is obtained by a camera that is moving along a straight line. Okay, you will have to have correspondences between 3 images to solve for this. Okay, we will talk about that more in with the averaging techniques. Yes.
So in this case that you are now presenting us in the increasing method, we just find the correspondence between 2D and 2D between the third image and one of the first 2 images.
Yes.
And then because we already know the connection between the 3D and the first 2 images, I can forward it to the third image. This is what you're doing?
Yeah, this is essentially what we do. So let's repeat this again and see. So let's sort of take the first step. Okay, so in initialization, we took image 1 and image 2, let's say. Let's call them image 1 and image 2. And we took pairwise correspondences, and we compute the second camera with respect to the first camera. So the first camera is the identity 0. The second camera is some rotation and translation. Okay, and we have a set of pairwise correspondences that we use to compute these cameras. Okay, and these pairwise correspondences give us some 3-dimensional points. That's what we did with the first 2 images. Okay, now we take a third image. Okay, the third image have features. Some of them correspond to image 1, some of them correspond to features in image 2, and some of them correspond to images 4, 5, 6, etc. Okay, I'm looking at the correspondences that are mutual, that they are both from image 3, the new image, to image 1 and to image 2. Okay, only correspondences that are common for all 3 images. Okay, these correspondences, we already know the 3-dimensional position of the points from the first 2 images. Okay, and so we can apply P3P and ransack and find the camera pose of image 3. Okay? That's the first step. This is this step. Use PNP to solve for camera pose. Okay? The next step is to take the correspondences between image 3 and image 1 and the correspondences between image 3 and image 2, which are not common, for which we don't yet have three-dimensional position because we didn't have correspondence between image 1 and 2. Okay? For these points, we perform triangulation. Okay? Which means that we use these pairwise correspondences to find the three-dimensional point and the three-dimensional positions for the structure in the structure that we already have. So this means that we augment our reconstruction with new points. Okay? Hope this is clear. Okay.
I have a question.
Yes, go ahead.
So basically, you take you have pairs for every two images. So
Yes.
for every couple inside these n images, you take pairs.
Yes.
And it's a reasonable assumption to assume that a point correspondence would also be between camera 1 and camera 2. I will have multiple of these points in the correspondences between camera 2 and camera 3, and that there will not be different points.
Right. So some of them will be different and some will not. So the idea, usually we will see some reconstructions in the next slides. Usually these databases are really, they contain many images, and many of them were taken from similar positions. And so there are many inliers, there are many true correspondences between the images, at least between those that are taken from nearby poses. And so it's not difficult to get tracks, okay? This doesn't work if you take a picture, really move quite a bit, then take a second picture, and then move quite a bit and take a third picture.
Ronen,
Yes.
In the second stage, when you do PNP, okay, you said that you're taking the common between all the images, right?
No, so I'm taking, okay, let's, if I understood your question correctly, wait a second and we'll get to that, okay? So let's just finish here first the fourth step. The fourth step is to apply bundle adjustment. So I want to improve my reconstruction. I want to improve the pose of the images, the cameras, and I perform bundle adjustment on the three views that I already handled. Now I will repeat. So I will go to the fourth image, okay? So I'm choosing a fourth image first, okay? Then I want to apply PNP. What should I have then? Okay, I need correspondences between the fourth image and two of the preceding images, okay? I don't need correspondences to all three. I need, in other words, I need correspondences between a point and a three-dimensional reconstruction. A three-dimensional reconstruction was obtained from pairwise correspondences in the original set. So the original set here now contains image 1, 2, and 3. And a three-dimensional reconstruction was obtained by triangulation of any pairwise correspondence in the three images. Okay, so really I only need correspondences between three or tracks of length 3 in order to perform this method. Okay?
Ronen?
Yes.
I'm not sure I understand what you do in the bundle adjustment step.
Okay, so the bundle adjustment, let's go back a slide. That doesn't move to in my screen. What happened with Zoom? It just doesn't work. Oh, okay. Do you see the? Okay, you see the slide, right? It shifted. Okay, so in bundle adjustment, I want to minimize this cost function. Okay, so I have some reconstruction, and I have some poses, and now I want to see, and there will be some errors here. Okay, the cost function will not be 0, and I want to simply minimize it. So I want to change the cameras and change the 3-dimensional points such that this cost will be minimized. Okay.
But what is the algorithm that you use to do that?
Merav, are you there?
Sure,
Something
yeah.
we saw
The
briefly.
algorithm that Amnon just taught us before 2 lectures, that
okay.
what we call the Gauss-Newton, November-Marquette,
Yes.
line search methods,
Okay.
the optimization.
So what we saw now is just the initial initialization, and afterwards we go to the. Okay.
Yeah.
Thanks.
Exactly. Yes. I wanted to make sure what you studied until now. Right.
I have a question about PNP and P3P.
Yes.
So, in I guess the second lecture, when we had
You're mute.
oh sorry, when we had 3D points and wanted to estimate camera parameters, we called that a resection problem. Is it this problem is PNP? So, what's the relation between like the resection problem and this PNP? Because as I understood, in the second step, we have some 3D points and we want to estimate camera parameters, right?
Right. I don't remember exactly which one is called resection. Resection is cameras, right?
This is camera resection.
P3P is one way to do resectioning. You
Yeah.
can do resection also with 2D correspondences, right? Like we did in one of our papers.
Actually, we had 2 kinds of camera resectioning. We had the projective case and the Euclidean case. The P3P is for the Euclidean case. And we had also talked about camera resection using DLT for the projective case.
Yeah, that's what I was talking about, like about.
So usually in the incremental SFM, we deal with calibrated cameras. If they are not calibrated, then there is some auto calibration step, or I ignore this in this class. Okay. Okay. So is it clear? More questions? So again, this is the pipeline, and you can already think about the problems that could occur with this pipeline. It's really critical to choose the first 2 views to be good views, ones that have enough overlap and give you good reconstruction. And the order of images afterwards is also important. But overall, this works very well. In fact, I mean, basically all of these techniques were already they already appeared in papers in the 90s. And this pipeline was presented in 2006 in a work that was called Phototourism. And what they did is that to take images from Flickr, which is an image data set that people upload, and used it to do reconstruction. And this was very effective. And since then, there were improvements over this work. So in 2009, the same group actually had...
Still in the second slide?
Sorry?
You're still in the second slide?
This is the second. There was this slide, 1, 2. This was the third slide. And now I'm moving. Building home in a day. You see this slide?
Yeah.
Okay, good. Okay, so this is a continuing work. So one of the problem is that this is a very tedious process. You go image by image, you reconstruct the cameras, the 3-dimensional points, then you do bundle adjustment, and bundle adjustment is expensive. And as I said in the previous slide, or wrote in the previous slide, bundle adjustment is expensive, and one of the tricks is not to use it in every step, but to align several cameras, several new images, recover the cameras, the structure, and only every few images apply bundle adjustment to save some time. But still, this was very slow. In 2009, basically using the same techniques, the same group applied what they did is really more of a show-off paper, where they took 150,000 images from Flickr. All of them are pictures taken from in Rome, and they did the matching and reconstruction. They used 20 hours of cluster time with almost 500 nodes, and they managed to reconstruct quite a few landmarks in Rome. And here we will see one of them. This is the St. Peter's Basilica, and you can see the quality of the reconstruction inside and outside. Okay, so all of these, you see here the pyramid. This is the one of the cameras. Let's see again. So see how many cameras there are. You can see, so basically tourists took many pictures, some of them in the second floor here. This was very impressive work. Okay. The next I want to talk a little bit about Colmap, which is a newer version of incremental methods. It's very effective, but as you will see, it's full of heuristics. We are going to go through some of them, not all of them, but it's quite efficient. So you can run on hundreds of points in few minutes only, and it's very accurate. So let's see what they did. The pipeline is the same pipeline that we presented so far, but there are many small things that are done on the way. So for example, there is a step that they call scene graph or augmentation, where they try to verify that between pairs of image there is no dominant plane or a situation of pure rotation, so that you want that every two views that you use will actually have some three-dimensional information between them. And you want to remove point matches that are due to watermarks and timestamps. In many internet images, there are watermarks and timestamps from video, and these give rise to erroneous matches. In the next view, best view selection, instead of looking on how many inlier matches there are between the new image and the reconstruction, what they count is they basically what they do is the following. They divide the image into blocks, squares, and all the points that fall in one block, they count only one. Okay, so they want not only that there will be many inlier matches, but that they will be spread all over the image as much as possible. Okay, so they count the number of blocks in which there are inlier matches, and they do that with several block sizes. Okay, so they divide the image into grids and count how many blocks contain inliers. Third, they try to do robust triangulation. Okay, so first, as before, they concatenate pairwise matches to produce longer point tracks. Okay, in the step of robust PNP, they use P3P and Ransack, and followed by applying DLT on the consensus set. Okay, like was mentioned before. And they accepted inliers under two conditions. First, that the point, so if you reconstructed the point, if you did the triangulation, okay, you want the angle between the rays from the point to the two cameras to be significant, to be large, okay? Because if the angle is very small, that would mean that your prediction of the depth may be subject to big errors, okay? So they accept only points where the triangulation angle exceeds some threshold.
Could you explain again, what is this angle? Between what and what?
So this angle is, take the 3D reconstructed point, okay? And that's XAB here. And take its difference vector, the vector from it to the center of the camera A and the center of camera B. Okay, the angle between these two vectors, so this is the ray from camera A to XAB and the ray from camera B to XAB. Okay, and this angle you want to be large. Okay, and also they check that the depth. Yes.
Why to use a large angle?
Again, so if the angle is small, if it's, let's say it's 0, if it's 0, it means that XAB lies on the same ray to TA and to TB. And then your triangulation is very sensitive, right? So the triangulation is more sensitive when the angle is small than when the angle is large. Okay, the value of the depth that you obtain will have larger error if the angle is small. Okay. And also they want to make sure that the depth is positive, what's called chirality constraint. I don't know if you learned this during the course.
Yeah, we discussed it, yeah.
Discussed it, okay, good. So, if the depth is not positive or if the angle is small, they rejected the point. Okay, and they didn't use it for now, at least. Okay. Then they applied bundle adjustment. In the bundle adjustment, they only looked at nearby images. So there were two different steps, one of local bundle adjustment and one of global bundle adjustment. So with every new image, they did only local bundle adjustment. Okay. And what they did is a variation of bundle adjustment with a robust cost function. So if you remember, bundle adjustment we usually do with L2 norm, right? They replaced it with this function which called robust Cauchy function. This is the function. So here you have L2 norm. The X represents the distance between the prediction of a point and its actual projection, okay? But you take the log of this. And this is how this function looks like. You can see that it's close to a parabola near 0, but that it converges to some constant. Actually, it goes to infinity, but it becomes a logarithmic as you go away from 0. Okay, where C is a parameter that tells you where, you know, this change from a parabola to a logarithmic function happens. Okay, so this is a robust function, if the distance is between the projection, the prediction and the actual projection is large, then the cost is not so high. Okay, so that's an outlier. You don't want it to affect too much your answer. Okay, so so in the bundle adjustment step, they minimize this function. Okay, then they filtered observations that had large reprojection errors. So these are the new outliers that they considered, applied retriangulation, and repeated bundle adjustment, and did this until no more observations were filtered. Okay. So that's the local bundle adjustment step. And finally, in the global bundle adjustment step, which they applied to the entire data set, but they could also apply it sometimes within the algorithm. Okay, what they did is they didn't apply it directly to all the images. Instead, what they did is to divide the images into many small overlapping groups of images based on how many inlier features there are between the images, basically looking at the intersection over the union. So how many common features they have relative to how many features they have with other images. Okay. For every group, they defined a virtual camera and aligned the images with respect with the virtual camera, okay, or computed the relative camera relative to the virtual camera, okay, and then they perform bundle adjustment with the virtual cameras, okay. So pi is the projection given the virtual camera G and the relative camera JG. Okay, image J relative to the G, which represent the group camera. Okay, and finally, the camera pose, the camera parameters for the Jth image is the product of the group camera and the relative camera of J relative to the group camera. Okay, so this way they saved time because the number of pose parameters was smaller in the global bundle adjustment step. And here you can see a reconstruction basically of central Rome, if you know the area of the Colosseum and all the Rome part with 21,000 images. I forgot to look how long it took, but that was much more efficient and robust than the previous papers that we saw. So that's basically the story with Colmap. Colmap is available for download. You can download and play with, and it's quite effective. Question?
You said that it has a problem when you are taking pictures on one line, if you are moving on a line, right?
Yes, we will talk about that in the next class.
This is because the local bundle adjustment, or because the virtual?
No. Are you talking? So maybe I didn't understand the question. Are you talking with the what happened when the cameras are moving along straight line?
No, I will fix my question. Okay. You said I'm taking angles, okay, big angles between two images, so I will get low error on the depth, right?
Yes, it's for any feature points, right?
This is the error is big because we are doing which step is following that give us this big error, because in I didn't know why in the previous method when we do it regularly, we can do it with a small angle.
No, we can do it. The question is how much error we get, right? I mean, as long as the rays do not coincide, in which case you need to divide by 0 and get infinity, okay? Then you can do this, okay? So basically, if there is translation between the image, between the cameras, then you should be able to do that, okay? The rays will not coincide. But if the translation is small, okay, or if the translation is the translation may be, I'm trying to think, for a certain translation, there are points that the rays are closer and rays that are further away, right? So for example, if I move to the right part of the image and the left part of the image, of the second image, will have the angle between these points will be smaller, okay? And so they will be less robust to reconstruct. And you can still reconstruct them, but maybe you will have larger error. And so the idea is to try to avoid large errors in order for the reconstruction to be more stable.
I'm asking because I'm thinking about my eyes, okay? My eyes doesn't have very big shift between them, and still I can reconstruct the depth, right?
Right.
So if I take my camera and I move a little bit, like my eyes, the distance from my eyes, I still need to be able to reconstruct the depth.
Yes, because the bandwidth between the two cameras is a part of the denominator of the equation. So if you reconstruct it using small bandwidth, the error will be large because you cannot compare the 2 points.
Right. So let me respond for the, to compare it to the eyes. The eyes, if you look at your three-dimensional reconstruction, you will see that it's very effective in a certain range. Okay, so if you look at very far points, you don't have good reconstruction. So you know that they are far, but you can't really estimate the distance so well. And the reason is that far points are, the angle is becoming small. Okay, so the further the point is, the more distant the point is, the angle is smaller, and your confidence of the depth is lower. Okay, or the errors will be higher. And that's exactly because of the reason that Shiran mentioned, which is you need to divide by the baseline, by the difference between the position of the camera. And that difference, the smaller it is, then there is more error. But really the ratio between the depth and the difference between the two cameras plays a critical role here. And that's what they capture with this triangulation angle.
Thank you.
All right. More questions, or we can take a break now? Let's take 10 minutes, 10 past 10, and continue from there. Okay, let's continue. So we talked about Colmap. Okay, and let me just finish by saying a few words about the advantages and disadvantages of Colmap. It's highly accurate. Even though the process is tedious, there is an efficient implementation that really works relatively fast. The disadvantages are mainly that the process is highly dependent on good initialization and next view selection, which are done pretty well generally, but still if the method don't pick the first two views well, or if the next view selection is not so good, then it won't work. And secondly, the overall it has many heuristics. They are tuned very well and they work very well, but this is somewhat a disadvantage.
Maybe I missed. What are the heuristics that this method has?
So we basically went through all of them. Okay, so there were, the fact that we remove certain matches, so there are, thresholds. The next best view selection is done on one way, right? So it's not a single optimization method.
Yeah, thank you.
Okay. Many parameters. Okay, so the second method that I want to discuss is the method of projective factorization. It's much less, I would say, much less useful, but it's sort of interesting more from a mathematical point of view. So let's see what happens there. Okay. So again, the problem is that we have point tracks and we want to find the cameras and the three-dimensional reconstruction. Here, we look at the usual equation. Okay, so given m cameras and n three-dimensional points, we know that the perspective projection equation is lambda ij, which we will call the projective depth. Xij equals pi times xj. Xj is the three-dimensional point. Okay. Now we will talk about projective cameras now, not the uncalibrated. Okay. Let's take this equation, the projection equation, and write it in a matrix equation. Okay, so the left-hand side is a matrix, lambda ij times xij. Okay, it's a 3m by n matrix because every point here, every term, lambda ij, xij is a vector of length 3. Okay, in homogeneous coordinates. Okay, this matrix is essentially a product of two matrices. The matrix of cameras P1 to Pm times the matrix of points X1 to Xn. Okay, you see, so if I want lambda 1, 1, X1, 1, I get it equal to P1 times X1. Okay. These matrices are of size 3m by 4 and 4 by m. Okay, so what can we say about W immediately if it satisfies this equation?
Maybe it's of rank 4.
Right. W has rank 4. Okay. Okay. If lambda ij were known, we could just use SVD to factor W into cameras and points, right? Now, this factorization will not be unique, right? It will not be unique because you can multiply the cameras by a 4 by 4 matrix and the points by the inverse of that same 4 by 4 matrix. Okay? But that's not a problem because multiplying the cameras by a 4 by 4 matrix is just like changing the global projective coordinate space in P3. Okay, so right, an affine change or a linear change is a 3 by 3 matrix in 3D. Here we have a projective space. In projective space, a 4x4 matrix up to scale changes the global coordinate system. Okay, so in a sense, this SVD factorization gives you a unique solution. Okay, but the problem is, of course, that lambda ij is not known. Okay, it is known, or it is constant, or essentially in the orthographic case, and that yields a Tomasi-Kanade factorization that whoever took the introduction course saw. I'm not going to tell you about Tomasi-Kanade factorization. If you don't know it, it doesn't matter. Okay, but in the projective case, we need somehow to find lambda ij. And the question is how to do that. Okay, so we will use fundamental matrices, and I want to show you something that will help us doing that. Okay. So suppose we look at two images, two cameras, A and B. Okay, A and B are 3x4 matrices, camera matrices. I just use A and B to simplify the notation. Okay, then given a point, a three-dimensional point X, capital X, we have these two projection equations, lambda AXA equals AX, lambda BXB equals BX. Okay, now we can take these two equations and put them in matrices. Okay, so the matrices look like this: A XA 0, B 0 XB times capital X minus lambda A minus lambda B equals 0. Let's see that this works. Okay, A times X minus lambda A times XA equals 0. B times X plus 0 minus lambda B XB equals 0. Okay, you see, this is just the same two equations written in matrix notation. And this matrix is 6x6. Okay, so A is 3x4, B is 3x4, so there are 6 rows, and there are 2 columns for XA and XB. Together, 6x6. Okay? What do we know about this 6x6 matrix? We know that it has a non-trivial kernel. Okay? This means that the rank of this 6x6 matrix is at most 5, and that the determinant of the 6x6 matrix is 0. Okay, so the determinant is 0. Now, if we open the determinant, right, how do you build a determinant? It's a sum of terms. Each term is a product of 6 values. Each of them comes from different row and different column. Okay, if you know this problem called the 8 queens in chess, right? You need to place 8 queens in different locations such that each of them has a unique row and unique column. That's how you build a determinant. Okay, so in particular, the determinant will be linear in the components of XA and linear in the components of XB. Together, it will be bilinear in XA and XB, right? And so we got a bilinear equation in XA and XB, and this is true for any choice of XA and XB that are projection of the same 3D points. So we got a bilinear equation in XA and XB for all XA and XB, and we know what equation is bilinear for 2 images. That's the fundamental matrix equation. And that's the only bilinear equation over all points. So this determinant must be the fundamental matrix equation.
Can you explain again why the determinant is bilinear?
Okay, so try to build the determinant. Let's say you go over the last column and you say, well, the first term is 0, so 0. Then you take minus the second term is 0, plus the third term is still 0, plus the fourth term. For the fourth term, you take the first term in XB, okay? Multiply it by by the determinant of the 5 by 5 matrix that is obtained by removing the fourth row and the last column, right? And that determinant, you start by choosing one element from XA and multiplying by the determinant of the 3 by 3 matrix that remain, okay? And this way you got a bilinear equation in XB and XA, okay? Okay, so this determinant gives you the epipolar line equation, the fundamental matrix equation. And in fact, if we check the components of F, they will be determinants of 4 by 4 matrices, which contain 2 rows from matrix A and 2 rows from matrix B. Okay, if we take, so we have 3 choices for 2 rows from matrix A, 3 choices from 2 rows of matrix B gives you 9 components of the fundamental matrix. Okay, and I won't show that, but you can try to derive it. If you look at the determinants that take 1 row from camera A and 3 rows from camera B, you will get an epipole. And again, so there are 3 ways to choose the first row here, and that gives you the 3 components of the epipole. And the same thing, the second epipole, you will get from 3 rows of A and 1 row of B. Okay, so this is sort of interesting. An interesting connection between the determinants of this matrix and the fundamental matrix and the epipole. And we're going to use it to determine the projective depth, if you remember. We'll remind you in a minute. So we wanted to initialize the projective depth. Let me remind you where we were, okay? We said we have this W matrix, and we wanted to factorize it into cameras and points. But to do that, we need the projective depth, okay? So we have the point tracks, Xij, from the images, but we don't have the projective depth. Okay, so we will look at a matrix that is similar to the previous one, but slightly different, okay? So given 2 cameras, Pi and Pk, okay? We have a 6 by 5 matrix now. Pi, Pk, that's 3 by 4 each of them. And the last column will be Xij lambda ij and Xkj times lambda kj. Okay? So these are 2 projections of the same jth point. Okay, the same point. Okay, in 2 images. Now this 6 by 5 matrix, you can see that it's actually rank 4. Why? Because I can write it as a product of Pi, Pk, the 2 camera matrices, and the matrix which contains the identity, and Xj, the 3-dimensional point. Okay, let's see. If I multiply Pi by the identity, I get Pi. If I multiply Pi by Xj, I get lambda ij, Xij. Okay, that's the projection position and depth. And the same Pk times identity give you Pk, Pk times Xj give you lambda kj, Xkj. Okay? This 6 by 5 matrix is of rank 4. If it's of rank 4, it means that if we take any 5 by 5 submatrix, it still have 0 determinant. It's not full rank, right? It cannot be full rank. So the minors, the 5 by 5 minors vanish. If I write these 5 by 5 minors, I get a system of equation, okay? This system of equation are linear in the lambdas, in the projective depth. Okay, and in fact, we take determinants here, determinants of PI, PK, right? The two camera matrices. And if you remember from the previous slides, such determinants give you entries of the fundamental matrix and the epipoles. Okay, so again, I won't go through the derivation, but you can imagine what's going on here. We get an equation that takes into account the fundamental matrix between picture I and K, Fik, okay, times xkj here. And this is the cross product within the epipole between image K and I and xij. Okay, and similarly, you can get the second epipole will give you more equations. Okay, so these are linear equations. So if I knew, so I know xij, if I can derive Fik, the fundamental matrix, and the epipole Eki, and given lambda ij, I can recover lambda kj. Okay. So what do? We take pairs of images, compute the fundamental matrices. Okay. From the fundamental matrices, we can compute the epipoles. Okay, these are just the null spaces of the fundamental matrices. Okay, and then we want to solve for the lambda ij's. How do we do that? We start with one image and say lambda ij is 1. Okay, so lambda ij will be recovered up to scale factor, a global scale factor. Okay, and then we go from one image to another. We should do that with a spanning tree. So for example, let's take the fundamental matrices between image 1 and image 2, then from image 1 to image 3, then from image 1 to image 4. That will give us all the depth values were up to a scale factor. Okay? You understand what I'm saying? Questions?
Could you please repeat the subscripts, the meaning, the notation here in the linear equation in lambda?
Okay, so we have this 6x5 matrix, and we know that it's rank 4 because of this factorization. Okay, this means that any 5x5 submatrix, the determinant is 0. Okay, that's what is written here. 5x5 minors vanish. Okay. So what I do is I take 5x5. So I have 6 5x5 matrices, right? Every time I choose one row and I eliminate it. Okay. And for these 5x5 matrices, I write the equation determinant of this 5x5 matrix is 0. Such determinant, when you open it, you have this column, open it by this column. Okay. So you take an entry from this column times the determinant of a 4x4 matrix taken from the camera matrices. Okay, such 4x4 matrices, that's what we saw in the previous slide, give you entries of Fik, the fundamental matrix, or of the two epipoles, Eki and Ik. Okay, the two epipoles. And that's how you get these equations. Okay, you see that they are linear in xij, xkj. Okay, and they are linear in lambda. Okay. Now, given that I know xij, xkj, and given that I computed the fundamental matrix and the epipole, I can recover the lambdas up to scale.
Ronen, in total, you don't have enough equations to solve globally for the unknowns lambda?
You have enough equations to solve. If you see the points in all images, you at least, and maybe even less, you have enough to solve for all lambdas up to scale. But let's go back to W and explain one thing, that is, we're dealing here with a projective setup. And in a projective setup, I can always scale all the rows and the columns here. Each row and each column by a different scale, and the reconstruction will be valid, will be still the same projective reconstruction. Okay, so really there is no point in solving this globally for all the lambdas, for all the points. Okay, good. So this is how I initialize the lambdas. And now we get to the final algorithm. So the objective is given xij, compute cameras p1 to pn, and three-dimensional point x1 to xn. Okay, and the pipeline is the following. First, we normalize the coordinates xij by using something like Hartley's normalization. You learned that, right? So we want all the points in each image to be centered around 0, and the variance of the point to be constant. Okay. Next, we compute an initial estimate of lambda ij using the equations that we just saw now. Okay. Next, we normalize the matrix of lambda ij. Okay, so we multiply each row to get a constant norm. Then we multiply each column to get a constant norm, and we repeat this. So if you know how you make a matrix bistochastic, that's a way, right? That's what you do. It's in a sense the same algorithm.
Can you explain again?
Okay, given the matrix of lambda ij, you take every row and you divide it by the norm. Okay, you make it norm 1. Okay, now the columns are not norm 1, so you repeat this, but now you go column by column and divide it by the norm to get norm 1. And then you repeat, you go back to the rows because you ruined the norm 1 for the rows, and these tend to converge. If the matrix was square, it will give you a bistochastic matrix, which means that it will converge to the case that the rows and the columns are all rank 1. Here, the matrix is not square, so really you need to divide to make them equal norm, but not norm 1. The norm should be square root of m, square root of n. Okay? Okay, so this is just a normalization step. It's not really important, but we use it because we want the process to be numerically stable. Okay, and as I said, scaling the norms of lambda ij or of the rows or the columns don't change the projective reconstruction. Okay, the fourth step is we form W, we take the normalized lambda ij, multiply by xij and get W. And now we apply SVD, assuming that the matrix is full, and take the first 4 singular values, 0 all the rest, and factor to get the cameras and the 3D points. As I said, it's up to a 4x4 ambiguity, but this 4x4 ambiguity just represents a global change of coordinate system. Okay. What I can do next is once I did this reconstruction, I can re-estimate lambda ij and repeat steps 3 and 4. Okay, and this way improve my reconstruction.
How do you factor the camera? You just take u and v, or you? Yes,
u times the square root of the singular values, and v times the square root of the singular values. Okay, so you need that the product will give you. In fact, any factorization will be good. Okay, that's the algorithm. Advantages. You solve simultaneously for cameras and points. The disadvantages, the matrices that you try to use can be very large if you have many images, many features, and so it's inefficient. It depends on good initialization of the projective depth. Handling missing data is difficult. You can't use SVD if you have missing data, if your tracks don't go through all the images. And incorporating Euclidean constraint is complicated, usually done in post-processing. Okay, so the inefficiency is often, some papers deal with that by subsampling points. So it's not ideal, but that's what they do. Handling missing data, you can do, so there are methods to find a low-rank factorization with missing data. This is more complicated to do, but can be done. Okay. Questions? Okay, the last part of this class, we're going to talk about averaging methods. We will continue in the next class, but we will start at least with we'll see what we managed to do today. Okay, so the idea is the following. Given images, what we want to do is to compute some relations between between pairs of images. But these relations will not necessarily be consistent, and we will want to make them consistent. So let's start with an example. Suppose I have here 5 images, and somehow I computed the rotation between pairs of images. Okay, so I know the rotation of camera 5 relative to camera 1, the rotation of camera 2 relative to camera 1. I build a graph. We call it the view graph or the scene graph. Okay. On the edges, I put the rotations with the right direction. So it's rotation of 2 relative to 1. The transpose would be 1 relative to 2, right? Etc. Now, each rotation here is obtained from measurements. So it can have some errors. And the rotations, therefore, may not be consistent. Okay. How do I know if this graph contains consistent rotations or not? Any idea?
Yeah, of course.
If you apply the circular consistency.
Exactly. If I go in cycles, I take cycles and just take the product of the rotations, I should get identity, right? If I rotate from image 1 to image 2, then to image 3, and then back to image 1, I should get identity. If it's not identity, it's not consistent. So I want to change the graph or change the rotation such that they will be consistent, such that every cycle will give you identity. It's not so convenient to work with the cycles. Instead, we want some algebraic constraints. So let's write this in algebraic terms. So we formulate it as like this. We denote Rij the rotation between camera I and camera J. Okay.
Ronen, we assume there is no translation here?
Yes. For now, we're talking, I said we start with example. We will see how it is becoming useful. But yes, for now, we're talking only about rotation. Okay. So, so we're given Rij, and that denotes the rotation between image I and image J. Okay. And let's denote Ri, the orientation of camera Pi in some global coordinate system. Okay. Now, the relationship between the orientation of camera I and camera J and Rij is given here, right? So the rotation, ideally, the rotation from camera J to camera I will be obtained by taking the inverse of the orientation of camera J and applying afterwards the orientation of camera eye. Okay, so to rotate from J to I first apply Rj transpose and then apply Ri. Okay, is this clear? This is the most important equation here. Okay, now we're going to play with this equation. Okay, we're given Rij. Okay, we don't know Ri, we don't know Rj. Okay, Rj transpose is the inverse of Rj. Okay, so what we will do is let's multiply by Rj. Multiply this equation by Rj, so we get Rij times Rj equals Ri. This equation is linear in the unknowns Ri and Rj. Okay, so what we will do, what we will want to solve is minimize over R1 to Rn of the difference Rij hat to, this is the measured Rij, times Rj minus Ri, and we take the Frobenius squared norm of this difference. Okay, this is a norm of a linear equation, linear formulation in Ri and Rj. Okay, but we have constraints. Okay, so we don't want to just find any matrices here. We want these matrices to be rotation matrices, and that means that for every I, Ri transpose Ri should be the identity.
What if we use like more than two cameras, like tracks of larger than three? Does it could help? Or?
Yes.
Here
Like,
we're using,
but it depends if you really know.
two cameras
Really read it.
Here is like cycles consistency of three. What if like we
I can't hear you. Somebody is not on mute. Please mute yourself. Okay. Shiran, say it again.
I say that here is a cycle consistency of three to go like from a global coordinates into the coordinates of Rj and then to Ri and back to the global.
Just as an example that it's three, but you need cycle consistency in any cycle. Okay, so this graph, maybe it's not even full graph. Let's say maybe we don't have this edge. We didn't measure the rotation between these two cameras. I still need this path to be cycle consistent. And essentially, if I take if all the minimal cycles are consistent, everything will be consistent. But okay, so but here in this algebraic formulation, I do it on n images. Okay, so I can do it in any, for any pair I have a term here, any pair that I have a measurement. Okay, and this could be sparse, so some pairs can be missing. Okay.
So Rj and Ri are unknown.
Rj and Ri, or really R1 to Rn, are unknown.
So if like some edges in the graph are missing, so you can still use them as a consistency if you increase the size of the cycle, right?
I'm hearing some other. Is this where you speak that there are more speaking?
Oh, okay, maybe please continue. So if you can't hear me, no matter.
That anyway, if I solve this, I solve the cycle consistency problem. Okay. Now this problem has quadratic optimization functional and quadratic constraint. So it's QCQP, difficult to solve. So one way to solve it is by doing relaxation. Okay. Okay. And so let's see a relaxation. Okay, the objective is homogeneous, right? Let's look here, right? We have Rj and Ri are the unknowns, so the objective is homogeneous. So we can just use DLT. Okay, we write a matrix here, and these are the unknowns. So the unknowns are R1 to Rn. There is this matrix, its size 3n by 3, okay? And this matrix, every time will pick, let's say, identity times R1, or let's say, minus identity times Ri, plus Rij times Rj, okay? So I'm just rewriting the functional in matrix notation, okay? And we want to minimize the Frobenius norm of this matrix. Is this clear? Okay. So this matrix, yes.
Again, you have only I and Rij.
Right. All the rest are 0. Okay, because I'm just re-implementing this equation. Okay, so each equation here involves only Rj and Ri. So I multiply an Rj by Rij and Ri by minus identity. Okay. So this matrix have rows 3 times the number of equations and columns 3n, okay, because we have n cameras. Okay, I want to minimize this. Okay, let's ignore the constraints for now. Okay, if I try to minimize this is DLT. I'm simply looking for the singular values, the singular vectors with lowest singular values, right? I need 3 of them because I have 3 columns here in the camera matrices, in the rotations really, not camera matrices, okay? So that's the solution, okay? And this solution has one more nice property. The columns of this recovered matrix will be orthogonal, okay? Because these are eigen or singular vectors, okay? However, the full vectors are orthogonal. We want each 3 by 3 blocks in these vectors to be orthogonal, right? Because we want to produce rotation matrices, okay? So by that, we did a relaxation, right? We didn't incorporate all the constraints. Okay. Okay, so we need an extra step where we project the solution, which contain the 3 singular values of 3 singular vectors of lowest 3 singular values. Okay, we want to project them into nearby rotations. What we do is we take a 3 by 3 blocks from this solution. Each of them we apply SVD, okay? And then eliminate the sigma, and our reconstructed rotation will be U times V transpose. Okay? That's the way you take a matrix and project it to become rotation. It really, we have to be careful here. We might produce a reflection instead of rotation. We ignore this, but we should remember this, okay? And we should know that because we broke it into 2 steps, we solve with SVD, with DLT, and then projected to get rotation, that by that, the solution will not necessarily be consistent, but it will probably be close to be consistent and maybe closer, and most probably closer than the point we started with. Okay, so this process is called rotation averaging. There are also other techniques to do rotation averaging. I just gave you one example. Questions about that? Okay, so how do we get rotations from pairwise images? What we do, we take pairs of images, compute the essential matrices. I'm assuming now that we have calibrated images. Okay. given essential matrices, we can decompose them into rotations and translations. Okay. But the problem is that when we do that, we have two solutions of rotations, right? Which are related by 180-degree rotation. Okay. So only one of them should be considered. Okay. You remember? I mean, questions about that? So how can we choose the correct one? The idea is to take triplets of views and see which of the two is consistent. So for a triplet of view, we have 8 possibilities, and we choose one of the possibilities, and that determines RIG. Okay.
You didn't say that t equal to 0?
Say it again. What equal to 0?
T, the translation.
Tij? No, I didn't say that. I only said that for now we only dealt with rotation. Okay, so this can be done even if t is not 0. You don't have to have 0. Okay.
Can you explain again how we can do it without t equal to 0?
Okay, so you take your images, you compute the essential matrices, you decompose them into Rij times Tij, okay, into rotations times translation. And now you consider only the rotation. You say you have 2 possibilities for Rij. You take triplets of images, you check what is closest to cycle consistency. What of the 8 possibilities is closest to cycle consistency, and that determines the Rij. Once you have the Rij, you go back to the algorithm and solve for to get consistent rotations. Is it clear?
Not really.
Okay. We have a few minutes. I will just start telling you about translation averaging, but we will probably repeat this next time. Let's see how we manage. Okay, so LUD is a method that applied averaging, and what it did is apply first rotation averaging in some different algorithm than what I told you before, but first rotation averaging, and then applied translation averaging. Okay, so again, in translation averaging, we are given translations between pairs of images, and we want to make them consistent. Okay. In practice, the essential matrix gives us translation, but only up to unknown scale. Okay. So we really need, when we do translation averaging, we also have to figure out the scale factors. Okay. Now let's assume that the rotations are already solved for. So now there is only translation between the images. Okay, that's what is done in LUD. Okay. So the Tij in this case, the translation that comes out of the essential matrix, are essentially a difference between the position of camera I and the position of camera J, Ti minus Tj, normalized, and the normalization, and also maybe in the opposite direction, right? We don't know if it's pointing in the direction of Ti minus Tj or in the opposite direction. Okay. Another way to write that is to write that Tij times the scale factor Sij, which can be positive or negative, is equal to Ti minus Tj. Okay. Now, if you remember, we could use feature points to determine the sign, but here I will not care about that. Okay, so the idea in LUD is to solve, to minimize somehow this equation. Okay, so I want to minimize the norm of Ti minus Tj minus Sij Tij, where the unknowns are T1 to Tn and the scale factor Sij. Okay, so this is very similar to what we did with rotation, except that, okay, now the translation should sum up to 0 if you go in a graph. Okay, that will be the cycle consistency of the graph. Okay, now we want to add constraints here. One constraint is that sum of Ti equals 0. This is like a global shift of the positions. Okay, we can choose arbitrarily what will be the centroid. Okay. Another thing is that we don't want, so one solution to this minimization is that we choose everything to be 0, right? I can, Tij is given, but I can choose the scale factor and Ti and Tj to be 0, and I minimize this equation. So I want to bound it away from 0. And I do that by requiring Sij to be greater or equal 1. Now, when I did that, that means that I have to determine the sign here. And so this is what I do. I'm using feature points to determine the sign. You studied that when you studied about the composition of essential matrices. I hope you remember. Okay. So this is the minimization problem that I want to solve. Okay. And they chose to use L1 here in order to be somewhat robust to outliers. Okay. But notice that this formulation is convex. L1 is convex, and inside this is linear in Ti, Tj, and Sij. Okay. The constraints are linear equalities and inequalities. So this is a convex problem. Okay, good. They suggested to solve it with iterated reweighted least squares, and that will be the last thing we'll do in this class today. Okay, what is iterated reweighted least squares algorithm? Okay, so we have some weights, Wij, okay, and at step 0, initialization, we just initialize them to be 1. Okay. And now we're going to minimize our cost function. So the cost function was Ti minus Tj minus Sij Tij. But now we minimize it with square. No. Okay. And with the weights. So at the first step, the weights are 1, and we just minimize the square norm of Ti minus Tj, etc. Okay. The problem is that we still have the constraints, sum of Ti equals 0 and Sij greater or equal 1. So this is a quadratic program, which you can solve. It's convex. I forgot to look how they solve it, so I will do that for next time.
Can you explain again why the sum of Ti is 0? Because you're taking centroid for the...
Right. I can take the centroid to be arbitrary.
It's a global...
right. I want to, in the minimization, I want to put it in some place. Otherwise, I have ambiguity, and you can...
I see. Okay. Thank you.
Be a problem. Okay, so I apply this quadratic program. Okay. I solve it. Now with W equal 1, okay? And next I'm going to update the weights. And the way I update the weights is that I take the square norm, I add some small delta, and I take this to the power of -12, okay? And I repeat. Okay, I'm solving a quadratic program with the new weights, update, etc.
How do you set delta?
delta is usually small. In theory, you want to make it smaller and smaller to approach 0. Now, why I don't use 0? If I use 0, I here divide by the square root of what I have here. And I don't want to divide by 0. Okay, so that's why I add a positive delta. Okay.
So if I understand correctly, so if you have like one term that is small, you increase the weight?
Yes, so the weight will be, so think of it, there's some points will have small values, some points will have big values. The weight of the big values will be larger. The small values will be smaller, but it will not be 0. Sorry, the opposite. You want opposite? Well, I need to think. We need to finish the class, so let me finish and then see what happens with W. But what I wanted to say, let's think for a moment what happened at convergence. At convergence, the W doesn't, so W doesn't change. The solution in step R and step R minus 1 and step R will be similar. Okay. If the solution is similar, and let's assume the delta is 0, then this term and this term are the same. Okay, the term before you apply the iteration, the term after you apply the iteration are the same. Okay, they converge to be the same. So now you take this square norm, divide by the square root of that. So you divide by the L1 norm of this. Okay, multiply by the square norm, you get an L1 norm. So this means that this will converge to the L1 norm, which is what we wanted, right? So in the previous slide, we wanted to minimize the L1 norm of this. So that's the way to think about this. That's the rationale of this thing. What we know about IRLS, I will not prove this here, that it's a majorization technique. And so the cost function cannot increase. And here, due to convexity, if you take delta towards 0, the optimization will converge to a global optimum. So this is, okay, so let me just say that LUD, this is the algorithm. It works first by averaging rotations, then averaging translations and scale by the method that I showed now. The advantage is it's a global method. You look at all the images at once, okay? It's non-incremental. It's relatively efficient because you solve only for cameras. You don't need the point features. And it's relatively accurate. Still, sequential methods are slightly more accurate. Okay. The main disadvantage is that you do this separately for rotation and translation. Next class, we will do it simultaneously. We will see how to do that simultaneously. And one note is that to increase accuracy, what they did is to estimate TIJ, they used feature points. So globally. And so that hurts efficiency, but improves accuracy. Let's not talk about the last point. I will talk about it next time. Questions? Okay, let's see.
Can you explain again, please? Again, the previous slide.
Okay. So we want to minimize.
And then can you stop the recording?
Yes, maybe I'll stop the recording.